Flow-based programming is a type of visual programming where you connect the inputs and outputs of various nodes. The idea behind it is to treat each node as a black box that has a specified task. You know exactly what should go in and what should come out. Whatever goes on inside is irrelevant until you come across some edge case that nobody thought about, the event that everything comes crashing down. By adding more and more nodes, you can increase the complexity, kind of like standard text-based programming, but in 2 dimensions. Today, I'll tackle making my own flow diagram creator, because I couldn't find anything to help my own use case. Of course I'm joking, you could use something like d3.js to generate interactive graphics that model a flowchart, but frankly, doing something like that makes way too much sense, so we're building it from scratch. In all seriousness, the previously shown Node-RED is really only for web applications, and while it is pretty useful and you can create and use custom nodes, I need something that can visualize different data types for potential future projects and not just programming. Now that that's out of the way, let's start with the foundations of our system, beginning with a node. Nice, now we want to be able to move it. Okay, that's pretty easy, just implement dragging with mouse down, move, and release functions. It would probably be better to wrap everything here into a class, but I can't be bothered. Right, next is panning, so we aren't stuck with this small area. We can reuse this code because it's entirely reliant on these 2 functions, which we can easily implement on a different object than a node. In this case, I have a special div for panning. The trick here is to have every node a child to the pan div. This way, we only have to reposition one element in the document with JavaScript, and everything else moves with it. On the release, we move the pan div back to its initial place and offset the node's positions by the total move. This way, the net displacement is 0 on the release, and the pan div is back to spanning the entire diagram for the next drag. It's about time to add some functionality. This involves having some sort of format to display nodes in with inner parameters to be able to set things and terminals to allow information to actually flow. After that, we'll want some means of importing and exporting diagram data. For node displays, I decided to use a template approach. This way we could standardize the general format of each node type, so maybe an AND gate will be represented by this template and correspond to this node that we can create as many copies of as we want. Within this template, we can modify where and what each terminal is, and there's even a nice little tooltip that displays the type. Okay, prepare yourself for the monstrosity that's incoming. Yeah, I think it's pretty easy to tell at what point I stopped caring about cleanliness. Regardless, these are the parameters, and they take in a JSON string in one of the following formats. I don't expect to put much time into the template, so something like this should be okay for me. Is the excuse, and I'm sticking with it. I should have probably added a bit more functionality to the formats, using more dictionary keys for things like positioning and sizing, but that's a problem best tackled when it comes back to bite me, and the next important thing is to have connections between nodes. I want to be able to click and drag from one terminal to another and create a connection between them. Each input should take data from only one output, and each output can output to multiple inputs. Perhaps in this way I should be using something like Blender as a flow diagram example as opposed to Node-RED, but I mean, that part's already done. So we have a couple of options for drawing the connections. We could use scalable vector graphics or the HTML canvas. I'll use SVG because changing endpoints on a Bezier curve, Bezier? What? Changing endpoints on a Bezier curve will probably be better than redrawing an entire canvas every time we either drag a node or pan the entire screen. Easy, right? Kind of. Okay, but before I got here, there's actually another big problem, so let's put this on hold. Take this little script here. We create a path element and put it under an SVG element that happens to have the very unique name of test. Every once in a while, we set the D attribute of path to have the top side of a Bezier curve move 1 pixel to the right. Oh, and also we have another path right here just to show that the SVG actually works. Well, as luck would have it, it doesn't. So let's coax it into doing something, maybe? Is it dead? Okay. The solution here is actually this. In examples of SVG inside HTML, there's an XML_NS attribute, which refers to a namespace. Namespaces are typically for disambiguation, at least according to Oracle, but in this case, whoever is responsible for rendering websites onto the screen needs to be explicitly told that everything under this element is treated according to the SVG specification. From the MDN web docs, we only need to do this once, because all the children of the SVG element will be treated the same way. In JavaScript, we would specify the createElementNS function to force a namespace. Because before, we were not specifying the namespace, whatever went on in here was not well defined. And here we go. So back to this, suboptimal behavior. Well, the easiest thing to do here is to just delete and redraw everything. I have each connection, what I call edges, to be identified by the index of the input node and terminal. Each output terminal has an array of inputs it points to, and each input terminal stores what output terminal points to it. So, to reference the edge, all you need to know is the input terminal and the node it corresponds to. But I also store the ID in the output node, just because. The problem with this is that the indices get messed up when a node is deleted. When this prior node is deleted, it offsets the indices of every node after it, and instead of looping over the SVG elements in the DOM and updating their indices, I find it easier to just delete them all and redraw them. Hypothetically, deletes will not be occurring very frequently, so optimization really doesn't matter here. Finally, we need to be able to save and load diagrams, which is kind of the entire point of doing something like this. Yeah, putting the I/O in implementation. The real joke is me thinking that was funny enough to put in the script. The obvious choice would be to use JSON strings to encode the necessary information to reproduce any given diagram, so let's figure out the format. Storing templates is trivial. We already have an object format for each template, which is what the code looks at whenever drawing a node. All of the template-specific fields are stored inside this one object for each template, so it would be best, and by that I mean least work, to just JSONify this object when saving the diagram, and parse it when loading. Nodes are a little more difficult. For the most part, we can just do the same stringify parse method, however there's one major problem to this. In the code, each node stores, by reference, the nodes it shares edges with. We need to convert between reference and some unique identification because the obvious choice for this identification is to just use the indices of each node, making sure that when saving to a JSON string, the order of the nodes is maintained, which isn't really that hard, but makes the exported format a bit fragile. This is what I ended up doing, but it may not have been the best approach. In the event that I want to merge two diagrams, using a string or some kind of universally unique identification would have allowed me to just append one node list onto another. Because I opted to use indices as identifiers, changing the node list would require looping through the edges and updating those ones as well, which isn't really that bad, it's just a bit bothersome. I should also note that when saving, I also need to clear out the edge SVG IDs from the outputs, as those are relevant as well. Either way, this blends down to making a deep copy, cloning our node array while modifying some elements within it. Loading the diagram is similar. After we convert the JSON string into an object, we can just modify the reference fields in the node list and initiate a draw call that will automatically produce the edges. Having a utility like this is nice and all, but on its own it's kind of useless, so clearly I need to create an equally useless use case for it. And by that, I mean a visual programming language. After a couple of hours on Notepad, I think I've come up with something more unintuitive than Scratch, which isn't saying much because Scratch is actually pretty elegant in its design, so instead I'll say on a scale of Python to brainfuck, I'd give it about an 8. I've decided to call this language Philosophy, mostly because that's what I titled this document after thinking, alright, I should put my thoughts and ideas on how this language should operate, and I need a better reason that doesn't appear like a pretentious, I know how everyone should program. There's only one way to do something correctly, and that way is obvious. And if you don't do it that way, you are a disgrace to all people who write code, and you should be put on a pike as an example to this forum. Also, you could probably find a lot of reasons why this language could be a metaphor for philosophy and some haha field of study bad sense of humor. On an unrelated note, a lot of these design decisions are arbitrary and are prescriptive for the very limited number of cases I could come up with in 2 hours. Some things that I did not think of during that time are not very easy to do, and I'll show a few cases later. Philosophy is centered around a flow of byte streams of arbitrary length. Each byte stream travels along the graph concurrently to other streams, allowing for pretty natural parallelization, which is ironic because JavaScript does not actually support multiprocessing. A lot of these features are exclusive in low-level languages, stuff like directly working with addressable memory and having only one data type, which is a binary string. But there's more high-level stuff like function declarations and calls. In terms of what I'll call the instruction set, I have 20 commands that have split into 4 categories. For I/O, I have the basic CLI functionality of reading from an input buffer and writing to an output buffer. These are akin to using scanf and printf in C or input and print in Python. Each one handles byte streams, in this case ASCII strings. After that, there's memory access in the form of load and store commands. These are like LDR and SDR instructions for an assembly language like ARM. For operations, I have the bit manipulations you'd find in an ALU minus floating point operators. Because this language uses arbitrary byte stream lengths, it doesn't really make any sense to use standards for floating point used in traditional computers. Also, because this language uses byte stream lengths, I have commands to get the length of a string by counting the number of bytes and set the length of a stream by adding or removing bytes. The largest category involves control flow, things like conditional jumps. Of course, something like a branch not equal instruction is pretty useless in the context of what is basically a flowchart, so a typical if statement works just fine here. There's a wait command to pause a stream if need be, a command to tell the program when to start, akin to the top of a file for scripting languages, int main for C, and public static void main string args for Java, and an end command to stop the program. I also have branches and merge instructions for handling any cases where there are ever constraints on the number of edges for each terminal. This last section is for things that are user-defined, stuff like macros and magic numbers, constants, as well as function declarations. Functions have their own scope, so byte streams spawned by different calls cannot interact. This allows for things like recursion and function calls from different locations in this code, pretty much like the stack for your more typical programs. To test this language, I've implemented various programs in Philosophy. This first one calculates the first n numbers of the Fibonacci sequence. Pretty straightforward. We initialize the first 2 numbers as 0 and 1, and then we begin a pretty hard to see loop to calculate the next numbers. On a side note, I don't actually initialize the first one to 0 because I expect the memory to be all zeros already. This loop in the flowchart carries the index of iteration. Notice how the number is checked to see if it is greater than or equal to the iters macro, and then incremented by 1. This addition, however, only occurs after the next number is stored. Inside this spider web, there are a few things happening at once. On the ith iteration, we get the ith byte in memory. At the same time, we're figuring out whatever I plus 1 is, which will then load that as well. As we add these 2 numbers, we calculate I plus 2, which we store the next Fibonacci number into, after making sure that it stays only 1 byte. Eventually, when we're done, we get the first 10 bytes in memory and end the program, which show up here. This brings us to our first inconvenience. In this case, the repeat command can't be used because our next iteration requires a result from the previous iteration. This task cannot be parallelized unless we use the closed form of the sequence, but I don't have floating point logic right now. The only way to have a sequential loop is to have a branch and merge loop that halts somewhere. I could rewrite the repeat command to be able to do something like this, and if I do, I'll utilize function calls and scope to isolate each iteration. But the main caveat to this is the keyword if, i.e. I don't really feel like doing that right now. Also, I don't have a function that prints a number because this write command treats everything as ASCII, which is why I resort to doing something like this, where the array of data is printed out in a more raw format, but it's still readable. This leads to the next program, though. Okay, less of a program and more like a library. This is a function that takes an integer and outputs a string. It's a recursive implementation that converts each digit into its ASCII counterpart, so we should first cover function scope. In a typical program environment, we have what's called the stack. If we hop into a function, there are usually local variables defined within it to be used only in that function. We can then reserve a block of memory just for that function. So in the case of nested calls, we can just go further down in memory and then pop those blocks off the stack when we return. So the variable a in this function doesn't interfere with the variable a in this one, which becomes incredibly important when we're doing recursion. Well, what do we do when we have multiple processes and streams occurring at once? The trick is to use a tree instead of a stack. Because each process stores its internal state, all we need to do is add another field that categorizes the scope of the process, and then ensure that different scopes cannot interact. I do this by listing each process as a child of the process that called the function, and then whenever there's a node with more than one input terminal, it only matches processes that have the same parent. We do this by iterating over the parent's list of children when looking for processes to match with. This makes function termination a lot easier to handle. If a process has no more children, then we can just end the function similar to how we end the program if no more processes exist. This prevents soft locking a process where it's waiting for something that will never come. Similarly, if one process encounters a func output node, we can treat it just like an end node, but in the function scope. All we do in this case is return that process's data and Anakin the rest of the children. In the context of our int2string function, the way we implemented digit retrieval makes toString only work on positive integers. We can just separate the last digit from a number by dividing by 10 with a remainder. Because of how numeric characters are encoded in ASCII, we can easily convert a single digit, so the byte value of this digit can just be appended to the ASCII string of the rest of the number. The rest of the number is handled in the exact same fashion. Once we reach a quotient of 0, we want to exit the recursive loop, and while we could technically treat this with a 0 in front and still be correct, nobody in their right mind writes this number as 0,123. We handle this case by returning an empty stream. While this makes the ASCII conversion correct for other single-digit numbers, if we pass in a 0, we won't actually get the number 0. So what we end up doing is handle all the cases in int2string and defer the recursion to toString. For 0, we can just return 48, which is the ASCII representation of 0. For positive numbers, we can just return the output of toString, and for negative numbers, we just toString the inverse and then prepend a negative sign. Alternatively, we could have had the terminating condition before the next toString call. If we checked if the quotient was 0 here instead, then this function would have handled the 0 case much better, because the 0 character would still be produced in the modulo section of code. Why didn't I do that? Because I didn't realize at the time, and something like that really doesn't warrant a fix. Now, what does warrant a fix is that I swapped between underscores and camel case in my function definitions, but instead of doing that, I'm moving on because I'll never use this code again. This last program is a bit more fun. Before making it though, I ended up implementing a display. This grid represents the first 100 cells in the environment memory, where each square is a grayscale representation of the corresponding byte. We'll implement bubble sort and watch the darker squares float up, as opposed to using int2string for verifying correctness. But first, what is bubble sort? We sort this array by doing a bunch of adjacent comparisons. Wherever two elements are out of place, we swap them. But we don't just randomly look for out-of-place elements. Bubble sort scans down the array. In most implementations, this is from the lowest to highest index. This way, we know the largest number ends up at the end after the first iteration, so the next iteration doesn't need to interact with the last element. In general, the ith iteration guarantees that the last I elements of the array are in their correct positions, so we only need to iterate n-1 times, because the last element has only one logical place it could be if everything else is correct. The comparison is pretty easy to do, and I've implemented it in the underscore function. It takes in a memory location we want to examine, what we'll index as I. We load the data in I and I plus 1. If the second number is less than the first, we store the first number in I plus 1, and the second number in I. Otherwise, we do nothing in return. This forces the largest number to appear on the right. I also utilize a linear congruential generator to get 100 random bytes, but don't worry about that. After the array is randomly populated, we begin the sort. That was 4 minutes. That was slow and unentertaining. Here's a more naive way of doing this. This method just does a bunch of iterations at the same time and goes through the whole array each time. It's prone to data deletion because this function is entered multiple times concurrently, so when one process is comparing two numbers, another process might modify them. If these two elements are swapped as this process is comparing these two, then this element is deleted and we get two versions of this one. However, at this point, I only care about how it looks, and it looks pretty cool. If I wanted to make this actually work, I would need to implement memory locking, which would probably be another command. Maybe something like this, where we input a section in memory, and then the environment doesn't allow memory access unless you are in the same scope as the process that locked it. While this was an interesting foray into visual programming, as well as constructing my own language, I don't think this is something worth pursuing with my time. So I'll end this venture with a list of a few more things that I could do if I was improving this language. First, web workers. This would have made it possible to run things concurrently as opposed to faking it. I would then have to ditch this tick function as a means of progressing the processes, or at the very least set up an alternative that could be used when desired, because ticking was very useful when debugging. Second, debugging was a nightmare regardless. All I had access to was the Chrome console, where I would list out all the processes. The processes hold the node index that they're in, but there is no way for me to figure out which node has what index unless I remembered exactly what order I placed these nodes. Or I could go into the element inspector and literally count from the top which node corresponds to a given index. Some means of visualizing either the node index or the process locations would be a godsend. Third, it would be useful to allow multiple files or pages for a program. If I wanted to use int to string somewhere, I would need to append that node list onto my project. It would be a lot more useful to just allow importing this JSON file and calling the function inside whenever I needed it. There is a reason why most programming languages allow you to use code for multiple files after all. Fourth, ditch this thing where we have only one data type. It was an interesting novelty, but it's gotten more annoying than anything. We're better off having more types. While it does sort of allow for multiple arguments to be passed into the functions using a few potential schemes, it's easier to have something more like what Node-RED does, where it passes around a payload that we can just access like a dictionary. The current scheme does not facilitate object orientation, so readability and workability take a massive hit. I do like arbitrary size data though, and if I were to put more time into this, it would be interesting to see what the implications are on fixed point or arbitrary mantissa arithmetic, where you could just set a precision you want and change it mid-program if you so wish. There are also some things that I want to do with the diagramming software itself, which I'll implement now or at some point in the future because it could be useful. For starters, zooming in and out is a lot more necessary than I first thought. Not being able to see the whole diagram of a function at once was really difficult to work with. This, however, requires me to rewrite a lot of the positioning code. Using CSS, we can transform elements. In particular, we can scale a div, and everything inside it will inherit the transformation. This allows us to modify the CSS of only one element, removing a lot of potential headache. Transformations are also pretty manageable with the use of this getBoundingClientRect method, which returns the bounding box for any element, all in pixel space of the browser. Right now, I have zoom bound to the scroll wheel, so at some point, I'll also need to implement the ability to set controls for people who might not have a mouse with one. Next, this type tooltip needs to go on the other side. So many times I've wanted to draw an edge and this tooltip covers up the terminal, so I end up having to drag my mouse off, wait for the tooltip to disappear, and try to hover on the terminal, but not the label. This becomes pretty annoying if I'm trying to work quickly. This will probably be the easiest fix to implement because it's just swapping a few CSS classes. Third, at the moment I only check for type equality. This was okay because I was only ever dealing with one type, a stream, so I never had to worry about stuff like inheritance. For other applications, I might need to pass in different types. For example, if I wanted to do some sort of optimization problem, maybe I'd want to pass a linear inequality constraint and a nonlinear equality constraint into the same constraint type. The fix would be to have a lookup table for each type, where we can look at a given type and see what can be passed into a terminal of that type. So an input terminal that accepts a constraint can just be given a type that accepts every constraint. Fourth, allow HTML/CSS overriding in a template, maybe even JavaScript. It would be really cool to have some sort of interactive visualization inside of a node. More importantly, it's a lot more flexible to the situation. I'll do this later because it's a lot more complicated and I'd rather wait until I have a better idea of what I want. Fifth, comment blocks and annotations. Every good programming language has a way of commenting your code so you don't have to decipher whatever you were doing 2 weeks ago. In that same vein, a flowchart is literally a visual tool to put your ideas down on, but there is no way to have notes here in this current state. Having some sort of block that you can place down to explain your thinking will be very helpful, because at first glance, I cannot be expected to know that this is a cascaded full adder. It might even be cool to allow vector drawing so you can circle certain parts of the diagram inside the program. I'll sit out on doing this as well because I would rather implement it when I overhaul the currently non-existent UI. Sixth, better edges. Right now, I have absolutely no control over where these lines go, other than to move the nodes themselves. This gets really annoying when there are just too many nodes to deal with and I can't tell which one goes where. I'll probably do this one when I add annotations because they both help with readability, and I'd rather wait until I can set dedicated buttons to this extra functionality. 7th, dark mode. I don't really think I need to explain this one. Right now though, I'd rather move on. This project has stretched out a lot longer than I planned it to, and I'm glad to call it done, even if there's an asterisk there. If I was more serious about the programming language, I'd need to have a whole team working on it, going through many iterations of testing and coming up with changes, and that investment really isn't worth it if I could just defer to a different language like I did with Python basically this entire video. Final verdict? You should never use this. If you do come across someone who uses philosophy in their day-to-day life, stay away from them.